And there's something to be said about being patient like that and wearing them down. All right, anyways, let's get started. Write out some of our highlighted equations, just really quick to remind us of them. This was a cosine kx minus omega t. Maybe write our omega. That one seems to come up a lot.
Yeah, that would be helpful.
Yeah, I got that one right. And maybe I'll just rederive our wave equation for us now to reset up the scene. Oh, we played with this. We remember what we called this thing inside of here. This is our wave equation. We call
your wave phase.
The phase,
Yeah.
the phase of the wave. Perfect. And when the phase of the wave is a constant, is when you're traveling right with the wave. So if you're traveling at the wave speed, then the wave phase is going to be constant relative to you. And we use that to derive another expression for velocity, which was the velocity is also can be expressed as
Omega over k.
Yeah. Omega over k. Good memory. And we could have also just substituted into this to get this. And maybe put k back up here, our wave number, which was 2 pi over lambda. Remember what lambda was?
Wavelength.
Wavelength. Okay. Are there any variables up there that we need to re-talk about real quick? Can't remember what they are.
The k.
The k, so that's the wave number, that's 2 pi over the wavelength.
That's right. And what is it? What's k?
We call it the wave number. It's how many wavelengths you can fit in 2 pi. So if your wavelength were exactly 2 pi, then k would be 1.
What is 2 pi? Is that like a time?
2 pi, well, that's typically the way that we think about a full cycle.
So full cycle.
Does a full cycle of a wave exactly come out 2 pi?
That still doesn't make sense.
Well, you can just flat out read it off the paper then. 2 pi divided by the wavelength. It's how many wavelengths you can fit in 2 pi. That's the wave number.
Why 2 pi?
Why not? Useful number. Why omega equal 2 pi f?
Because circles.
No circles in this. But we just think about 2 pi as being a full cycle. And so it's often related to a full cycle.
Isn't the wavelength a full cycle?
Yes, the wavelength is the length of a full cycle.
So the length of a full cycle underneath the length of a full cycle.
No, it's like if the wave, because I could have a wave like this, and I could have a wave like this, right? And maybe this is 2, this is 0, here's 2 pi. That's meant to be a full wavelength. This has a wave number of 1, this has a higher wave number. This has a wave number of like 2.
So is 2 pi meters?
Yes.
Okay.
Has to have the same unit. I didn't specify that, should have specified that, good question. It has the same units. I think. No. 2 pi doesn't have any meters, it's just a number. But whatever the units are just what are going to make this work. So let's see. So 2 pi, you actually have to think about that as radians in order for this to make sense. Because x is a meter, so this is 2 pi radians per meter. Because you have to think about that as radians per meter times meters just gives you radians. That you still think about radians per seconds times seconds just gives you radians. Radians minus radians is radians, cosine of radians.
Okay.
So still have to think about it as radians over lambda, or over meters. But it's just a useful quantity. Just something you can substitute in. Let's see. Okay, so next week we're going to come up with the wave equation as a recap. So when we have a wave, our position function, we have it right here. Here's our position function. right?
Yes.
And what we did is I said I'm going to take the partial derivative of this with respect to x twice. I'm going to take the partial derivative of this with respect to t twice. Maybe remind ourselves of that equation a little bit. Remember that there's two different ways that we can think about modeling a wave. We can model a wave with respect to x. So here's our y, here's x. And so this is like taking a picture of a wave, right?
Mm-hmm.
And then we can also model a specific point on the function, on the wave with respect to time. So I can do y, I can do time there, and then I can still model what a single point does with respect to time, right?
Yeah.
And it's the exact same, right?
Not necessarily now.
Why not?
Because this is seconds and this is meters. There's a way to shift this to make them line up.
Yeah, that makes sense.
But it's not necessarily the case that just because in 1 second it went from here to here, then this right here is 1 meter.
Oh, yeah.
Okay, that's what I mean. So, but they're both going to start out at the same peaks and shift. Well, depending on what point this is talking about. Because is this talking about this point, this point, this point? This is just some point. And the way I have it drawn here, it's like we're talking about this point right here, going up and down with time. But I could have easily just been this point right here, going up and down with time. Right?
Yeah.
Okay, so while we're calculating these values, let's also get intuition for what they represent. So first off, since we'll start by thinking about this picture, so I'm going to take the partial derivative of this with respect to x. So I'm looking at delta y, delta x, the partial derivative of y with respect to x. How do we do that again? We treat x like it's the only variable,
Mm-hmm.
That's right.
right? So this is going to be negative because cosine, derivative of cosine is negative sine. So negative, when we do our chain rule, we'll get a k out of there. Negative k a sine of kx minus omega t. Did I do that right?
Yeah.
Okay, so what is delta x with respect, or what is dx, what's the derivative of y with respect to x? Partial derivative of y with respect to x. Intuitively, what is that? For some point x, that gives you the slope here. That's the slope on this function.
Slope?
Yes.
Okay.
Yeah, that makes sense.
Delta y over delta x.
For any point though, right?
Depending, pick an x, pick a t, gives you the slope at that point.
Oh, yeah.
Right? Similarly, the second derivative, second partial derivative of y with respect to x, second, that's equal to negative k squared a cosine kx minus omega t, or in other words, it's equal
Your
to
position.
negative
Yeah.
k squared, our position, x. Anyways, so the second derivative here gives us a concavity at any point, whether it's
Yes.
concave up or concave down. It's concave up here, concave down here, concave down here, right?
Mm-hmm.
What does the derivative of a cosine graph look like?
A sine graph,
Negative sine graph, though.
a negative sine here.
So would it be the same as a cosine?
No. It'd be a shift of the cosine, but they're different. Negative sine and cosine are not the same thing. Negative sine, if we were to draw a negative sine here, negative sine, first off, starts out at 0, right? And then it goes down rather than up. So it goes like this. And that's the slope at each point. Notice that the slope here starts out 0, if I would have drawn this right. And then the slope becomes negative, negative, negative. You have your max negative slope right there, slope of negative 1. Then your slope comes back to 0. Then your slope starts getting positive, positive, max slope. And then your slope gets smaller and smaller, back to 0.
Okay.
Good?
Yeah.
Okay, and then we look at our partial derivative now of y with respect to t. And what does this give us intuitively? Well, I guess we can write it out first and then talk about it. So let's see, if we treat t like it's a variable, we're going to get a negative omega out front, but when we take the derivative of cosine, we get negative sine. So we're left with positive omega a sine of kx minus omega t, right?
Mm-hmm.
Now, intuitively, that gives us the slope of this function, the one down here, right, at any point, which is also the velocity of this thing. So we could also call this the velocity in the y direction. It's how fast the particle's moving up and down.
Yeah.
Makes sense why this one isn't velocity, this one is velocity. This is how it's changing with time. This is how it's changing the slope when you took a picture, how the slope changes.
So is that
Okay.
Huh?
What does that mean? The other one's velocity. What's that one?
It's just the slope if you took a picture. Take a picture of the wave at some moment in time,
I'll just give you.
go to some position, measure the slope, that's what this gives you. Which is not the same thing as measuring the speed that something's moving up and down. That's what this gives you. Remember that this is over a lot of time for just a single point. This is just a picture of the wave at a single instant. So this is time equal to some time t1. This is x equal to some position x1. So two different quantities. It's easy to get confused back and forth which is which. You need to be changing with respect to time to talk about a velocity. This is a picture, it's not changing with time. It's a snapshot.
Yeah.
Okay. And then we have the second derivative of y with respect to t, partial derivatives. That one's going to be equal to negative omega squared a sine kx minus omega t, which is also equal to the acceleration in the y direction, which is also equal to negative omega squared x. Right?
Yeah.
So then, to build our wave equation, we looked at the quotient of this and this with each other. So, I look at the second partial derivative of y with respect to, I can't remember which one was on the top. Hopefully it's not going to matter here. Don't seem like it should.
T is what you did yesterday.
Did the t there?
Yeah.
Yeah, we'll put the x. I actually think it's going to be easier to see how we continue. It shouldn't matter. The ratio is a ratio. Over the partial derivative of y with respect to t squared. And that is going to be equal to
Negative k squared x.
negative k squared x all over negative omega squared x, right? And we see that v is equal to omega over k, right?
Yeah.
This is k squared over omega squared, so that's going to be 1 over v squared.
Okay.
And the x's cancel out, right?
Mm-hmm.
So now move this to the other side, and we finally get our wave equation, which is the second derivative of y with respect to x is equal to 1 over v squared times the second partial derivative of y with respect to t. And that's our wave equation. Yeah. Okay, that's all right.
Okay.
And just like our simple harmonic equation, remember our simple harmonic equation was some constant, called k1, times x plus some other constant called k2 times a second derivative of x with respect to t squared equal to 0. Whenever you had an equation like this, you had simple harmonic motion. Anytime your position function satisfies this thing, your position function is talking about simple harmonic motion. Similarly, anytime your y function here satisfies this thing, your y function is a wave.
Okay.
That's what we mean by this, the wave equation. Same way we call this a simple harmonic equation. Good on that?
Let's go for
Yeah.
Sorry.
longitudinal waves too.
Longitudinal or transverse doesn't really matter. It's just that longitudinal waves, it turns out this y is in the same direction as the x.
Okay.
But everything still behaves the same. Okay, so now talk about the speed of a wave. We'll leave those variables up there, just need to make reference to them. and talk about pulling up on a string and how fast the wave travels through it. Now you have intuition for how you get the wave to go through the string, right? You pull up on it, and it starts sending that signal down through the rope, and the rope starts moving up since you pulled up.
Yeah.
And how that part of the rope moving up is traveling is essentially your wave speed, however fast that thing's moving.
But it's not really a wave.
It's not really it is a wave. It just doesn't behave with it's not a sinusoidal wave, is what we would say. If you just pull up, you'd have to pull up and down to create a sinusoidal wave. You'll have to keep using some frequency. But it is still a wave. Remember, what is a wave? When we're talking about a physical wave, what's a physical wave? It's when you send energy through some medium.
Okay.
So when you're transporting energy through some medium, you're sending a wave.
Gotcha.
So when you pull on a rope, that's a wave.
There is a wave of energy that's sent through the rope. You pull right here, which stretches the rope out, and it's like a longitudinal wave sent internally throughout the rope. Now, it happens really fast, and the speed's very fast, but that's essentially what's happening. The pull here is communicated to the pull here, is communicated here, 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 and it's sent all the way down to you.
Okay.
Okay, so let's draw our picture now for the simplest case. So we've got some rope. The rope was straight, and now we've started pulling up on it. And the part, since we pulled up, it's communicated that far on the rope so far. So we have this rope, and we're pulling up on it right now. So this, as we pull up, this point is moving to the right.
Okay. That's really oversimplified, right?
It's essentially what's happening. I mean, the fact that you pull up on a rope, the fact that you come back down, this point doesn't know that you came back down. It just keeps on moving along. That just changes the shape of this part over here.
Oh, I see.
But it doesn't always make it to the end, whereas the other one can.
It doesn't make it to the end because of heat and stuff like that, internal friction. But in a completely ideal scenario, it would make it all the way to the end. Once you pulled up on the rope, that would make it all the way to the end.
Yeah, that makes
And
sense.
how come when you look at it, it does? And when you just pick it up, it doesn't?
You're putting more energy into the system, which makes so it doesn't dissipate as much. Look, I'm doing work. Essentially, how am I putting energy into the system? I'm doing work. I'm applying a force up and down over some distance, which is doing work on the system, putting energy into the system. So the more energy you pump into the system, the more likely it is to make it all the way down there.
Yeah, that makes sense.
But if we had a completely ideal string, nothing was lost, it was pull tight between you and me, and I pull up like this, that's going to be sent all the way down the string. Okay. So here's our point P, that's what he calls it, and it's moving this way down the string with some velocity. We'll call that just V for our velocity. We're over here. This is the part of the string that we're holding. There's some tension in the rope. There's some tension in the rope, so it's being pulled at this end with some force. Try and make a clear thing there. It's being pulled at this end with some force F to create some tension in the rope.
Okay.
And so over here, we're pulling up on this thing. So we're pulling with some force. What does he call it? He just doesn't label it. He already breaks up into its components. We'll just call it, I don't know, T. Some tension that we put into the rope. And you can break this up into its components. It has its component in this direction, which has to cancel out this force. So this component is F, right?
Yes.
And it has then an up component, which I guess we'll call F in the Y direction, and now we've used up that T. So we have these two forces. That's just canceling out that, and then this is what's causing the rope to move up.
Okay.
And this is traveling through with some point B, and we can talk about the rope. This part of the rope, doesn't matter which part we talk about, is then traveling up with some velocity. Call it V sub Y.
What about gravity?
We're going to ignore the effects of gravity on this rope.
Okay.
Or we can say that Fy is strong enough that it's canceling out the force of gravity with this much left over. Probably a better way to say it.
Yeah.
Okay. So now, little bit of a throwback here. Going back to when we were talking about momentum, momentum. Momentum is mass times velocity, right?
Yes.
And the derivative of momentum with respect to time is equal to mass times acceleration, which is a force.
Yes.
So when we take a force then, and we multiply it by some time, so when we take a force and we multiply it by some time, that gives us some change in momentum. When you apply a force for some interval of time, you're left with a change in momentum. In other words, if I integrate a force across some time,
Okay.
then I'm left with momentum. When we take the derivative of momentum with respect to time, you get a force. When I integrate force across some time, I'm left with a change in momentum.
That makes sense.
Okay.
But you're just multiplying by t, that's not an integral.
T represents some interval,
Oh,
right?
yeah.
Because we say integrate f with respect to t across some time, you're going to replace f with some t, and it's going to give you some change in momentum.
Yeah.
Okay. So that's the crucial bit to understand for why this next equation makes sense. So I'll write it up here and then make sense of it. So we have f of y times t. T in our scenario is how long you've been applying the force. So t equals 0 is when I first start lifting up on the string or rope or whatever it is, start pulling up on it. And so sometime t is however long it took to lift it this high.
Okay.
Okay, so that's what t is. And this has to be equal to, so we have a force times the time that we've been applying that force. That has to be equal to the change in momentum to the part of the rope that's moving.
So your point P?
No, this is the part of the rope that's moving, right?
It's all moving?
Yes, every part of this rope is currently moving up with the same velocity vy.
In this snapshot in time, right?
Yeah, this instant time that we took a picture of.
Okay, that makes sense.
So the whole rope is moving up with the same velocity vy.
Okay.
There's this much of the rope, and so if we call the mass of this portion of the rope, we'll just call that m for now. And it's going to be m times vy.
Mass time.
That's the total change in the momentum because the momentum in the beginning was 0.
Oh, I see.
So the change in momentum is just the final momentum.
Okay.
Okay? Now, let's say that our rope has what do we call it? Not a density, but mass per unit length. You remember what we call that? Because I don't.
That's pretty good.
Yeah, so mu is what we used when we talked about kilograms per meter. So mu is kilograms per meter, and this rope has some mu. It has some sort of density.
Oh,
However
density.
many kilograms per meter.
Gotcha.
Okay.
So I'm going to use mu as kilograms per meter for this rope. Because I don't want to just use m here. I want to express it in terms of the density of the rope. You with me? So now, if this distance right here is d, then the mass that we're talking about, is equal to d times our density of our rope. Sorry, that's supposed to be mu.
The length times the density. Okay.
The length times the density gives me the total mass of the rope,
Yes.
right? Now d is the distance this point P has moved in our time t. Because when I first started lifting the rope, P was right here, right? And P's been moving that way with some velocity v, as I've lifted the rope.
Yeah.
So, d we can also express as, that is, the velocity of the rope times how long I've been lifting.
Okay.
Velocity times time gives you distance.
Yes.
So I can also represent the mass here as I'll put mu first, mu times v times t.
Yeah.
Okay.
Okay, we'll try and make sense of whatever you're saying there in a second. And so when we substitute that into our equation, now we can rewrite our equation as f sub y is equal to mu times v times t times vy. Right? I just substituted out m,
What is
the mass.
Well, now you have two velocities multiplying each other.
Yeah, we have a velocity this way. The one velocity is this velocity, one velocity is this velocity.
Oh,
Because those aren't necessarily the same.
yeah, they're not.
And you finding the change of momentum? Did that change?
We're ultimately interested in this velocity. Sorry, probably should have made this more clear. What we're trying to come up with an expression for is how fast waves travel through a rope.
I thought they were constant.
They're constant for some medium. Sound waves, you already know they're not constant. When you and Jeremy are holding a hose and you just go like that, it doesn't send the wave to him near as fast as if you pull hard and do it.
Oh, yeah.
Right? Increasing tension sends it faster.
Okay.
So whatever the velocity is, whatever it's equal to, when we ultimately figure out this v, you intuitively know that somehow force is going to be positive in this. The bigger the force, the bigger the velocity.
Yes.
And you also know that the heavier the rope is, the more mass the rope, the more massive the rope is, the slower the wave goes.
Yeah.
Right?
Okay.
So we somehow expect mass, or our mu, to somehow be down here. That should make the velocity slower, and the force should somehow make the velocity bigger.
What about tension?
Tension is part of it, the force.
Yeah.
Force, tension, whatever. The more force we're using, the higher we expect the velocity to be. The more massive the rope, the slower we expect the velocity to be. And so we expect it to be something like this. This is not the right equation. I'm just
Helping us get
throwing
intuition.
intuition on the board.
Okay.
So ultimately, we're trying to figure out what this v is.
Mm-hmm.
How fast the wave is going through the rope.
Well, then you just divide f of y by all the other stuff, and that's how you get v, right?
Well, yeah, we could just solve this for v so far, but maybe there's more information we can use to eliminate more variables.
Oh, I see.
And maybe that's a bit complicated still. Sorry, what?
What if you divided f of y by t? Then you could substitute. Right? Because you have your equation.
Well, we're still missing some insight. There's another equation we can use to help us eliminate our variables here. And that is noting the fact that our tension that we pull with is in the same direction as our rope,
Mm-hmm.
right? We have a different color. I don't want to make you think this has anything to do with the physical scenario. I just want to help you see the geometry. This angle right here is the same as this angle right here,
Yes.
which means that this triangle right here is similar to this triangle right here.
Mm-hmm.
But why do we care?
Why do we care? That means that this right here, we were calling this d before. This right here is d, or maybe we'll express it differently. This distance right here is velocity times time.
Yes.
This distance right here is the velocity in the y direction times time.
Okay.
And then this distance right here is f sub y, this distance right here is f. You with me?
Yeah, I think so.
Okay, so then we know that the ratio of this to this is the same as the ratio of this to this. So we know that f sub y over f is equal to v sub y of t over v.
V of t or just v?
V of t, thank you.
Okay.
I was thinking t's are going to cancel out. T's cancel out.
Oh.
And so we have just this expression. Now I'm going to solve this expression for f of y. And what do we get? So I get f sub y is equal to f times v of y
All over V.
all over v. So, rewriting this now with our expression for f of y plugged in here,
Okay.
then I get f times v sub y over v is equal to mu times v times t times v sub y, right?
Yes.
So we can cancel out the v sub y on both sides. We'll move the v over here. So let's see, we get f is equal to mu times v squared times t. Uh-oh. I think our t should have canceled out somehow. Oh, I just stopped writing it. F of sub y times t, and then I just didn't put t here.
Oh. Okay, I see.
Okay. So t goes there, which means we should have had an f times t here, right?
Yes.
And now the t's also go out. You with me?
Mm-hmm.
Okay, so then we're done. So now v squared is equal to f over mu square rooted. Oops, v is equal to that.
Okay, I see.
Really, we should have a plus or minus here, depending on are we sending the wave this way or this way, right?
Yeah.
Two possible ways that the wave can be moving.
So once you have your force and your density of your rope, then you can find velocity?
Yeah, force, but it's just the force that's resisting the pull. It's just this F. It's not how hard T you pulled the rope.
So it's dependent on whether you're tying the rope around the child or around the rock.
I don't know how to make sense of that.
I'm saying, like,
Sorry, are you missing anyone?
No.
if you pull the child, you're pulling the child, but the rock stays put.
Oh,
Saying the
sure.
force resisting you
Yeah.
is, okay.
Yeah. The more tension you create in the rope before you start lifting, the faster the wave's gonna go.
Okay. That makes sense.
And then the more massive the rope, the slower it's gonna go, which appeals to our intuition, hopefully. Anything weird there?
No, that makes sense.
Okay, now this was just calculating the speed of a wave, of a transverse wave. Transverse wave meaning the direction of the wave, or the direction the thing's moved, is perpendicular to the direction the wave moves. The wave moves this way, but the medium moved this way, right?
Yeah.
So that is just the velocity of a transverse wave. Now, it turns out in general, almost sneezed. That velocity for all sorts of different waves, as a general rule, can be represented as the square root of the restoring force divided by, what's the best way to say that? The inertia of the system. Its resistance to move.
The inertia?
The inertia meaning its resistance to move. One thing we could talk about mass, we can say mass is like linear inertia. Mass is your resistance to be accelerated forward or backwards,
Yes.
right? And then moment of inertia is your resistance to spinning motion,
Oh,
to
I
being
see.
rotated.
Yes.
So inertia is your resistance to whatever the force is being applied.
Okay.
So obviously in our scenario, what was causing it to resist? The mass of the rope. So that's what showed up down here. And the restoring force, what was trying to straighten it back out? F. What was trying to get back to equilibrium? F.
So inertia of a rope is just the density?
Well, no, the inertia of a rope isn't just density. The inertia of the rope is its whole mass. How can I make this appeal to your intuition? But with sending a wave, it doesn't matter if it's an ideal system and the wave doesn't dissipate at all. It doesn't really matter how long your rope is.
Yeah.
So in this scenario, all that really matters was the density of the rope. That's what's only going to be resisting your wave.
I see.
So as a general rule, to say the inertia of a rope is just its density, it's kind of contextual. What matters, what doesn't. If we were talking about lifting a whole rope up into the air, now how long the rope is matters.
Yes. Okay.
So it's just what's resisting the motion. And in our scenario, it turns out it's just the density that matters when it comes to resisting motion.
In an
And the
ideal
length of the
scenario.
rope doesn't really matter.
Okay.
Okay. Okay, so now let's talk about, well, I guess we can do the example problem and then talk about the energy. And maybe you just throw that over here really quick. So we just barely found out that the velocity in transverse wave is equal to the square root of F over mu, where F is the tension in the rope before you started lifting.
Okay.
Okay, our example problem. One end of a 2 kilogram rope is tied to support at the top of a mine shaft 80 meters deep. The rope is stretched and taut by a 20 kilogram box of rocks attached to the bottom. Okay, so we've got some mine shaft, and we've got some rope, and some support here, some rope that goes down into the mine shaft. And down here at the bottom of the mine shaft, we have a 20 kilogram bucket. So 20 kilogram bucket down here, here's our rope. Our rope we know is 80 meters long. The geologist at the bottom of the shaft signals to a colleague at the top by jerking the rope sideways. What is the speed of the transverse wave on the rope? So the guy at the bottom, he's putting something he knows into the bucket. When he's ready for the person at the top to lift the bucket out, he wiggles the rope to send a wave up the rope. How fast does a wave go up the rope?
Okay.
So the velocity, the mass of the rope we also know. The mass of the rope, we were told, is 2 kilograms. Right?
Okay.
So if the mass of the rope is 2 kilograms and the rope is 80 meters long, what's the density of the rope?
Density is just the length times it, right?
No, 0.4. 0.04? 2 divided by 80.
2 divided by 80 doesn't magically put a 4 up top.
Yeah.
So it's 1/40th.
Okay.
I knew there was a 4 in there.
There's a 4 somewhere. You can always express a number with a 4 in it. And give me a number, I'll express it with a 4 in it.
What about I? Oh.
Alright, anyways. So mu is equal to 1/40th
So that's your force.
kilograms per meter. That's our mu. What's our force on the rope? Because we know that velocity is going to be equal to our force divided by our density. So what's the force on the rope?
It's mass times acceleration, but what's your acceleration?
How hard is this rope being pulled down?
By 20 kilograms
Times G.
times G.
times G.
Plus
Yeah,
the
okay.
2 kilograms of rope, right?
Remember in our problem, F was the force at the right end of the rope.
Mm-hmm.
So the force here on the rope pulling down is not including the weight of the rope. That would be up here.
Yeah, that's
Okay.
So the force here is just 20G, and then we have that divided by 1/40th. Right?
Yeah.
right. Does it matter how hard he wiggles it?
Doesn't matter what?
Like he's just shifting it left and right. Does it matter how hard he does that?
How fast?
Yeah.
No, remember in our equation, F sub y didn't show up in there, V sub y didn't show up in there. Those completely canceled out. Probably should have shown that better, made that more clear. Where's my calculator? Keep waiting for you guys to get your own, so I don't have to worry about this anymore. With regards to that, you're the worst class I've ever taught physics to.
You've taught physics before, right?
Kind of.
Okay.
I taught trig-based physics.
Sad.
So this is your first calc base?
Yeah, this is the first time I'm doing this.
Do you like it?
I do. There's things I don't like about this book. I don't know that I'd ever use this book again.
Okay.
I don't like the order of some of the material and some of the focus. I really liked the other book that you used, but it was just trig. So I need to go find that book, find the authors, and see if they have a regular physics book. If I ever even do this again, who knows?
Yeah.
Good chance this never happens again.
Cool. Okay.
Not really.
Means you can do other stuff.
Yeah, but there's only so many things you can teach high school students. And this is, of the things that you could potentially do, this is some of the more challenging material, which makes it more fun to do.
Yeah. But would a lot of people believe you could teach high school students calculus?
Yeah, happens all across the world.
Yeah.
Really?
It's called AP Calc, Advanced Placement. So they have advanced placement students who, yeah, they do material just like this. When I was going to university, one of the kids I was going to university with was still a high school student, and he just had worked something out, so he was taking university level classes.
Dang, that's
And
cool.
so he, I don't even know if he graduated from high school technically, but he graduated with us, and he graduated at 17 with his degree in mathematics.
Okay. What a
Smart
cool.
guy.
Yeah.
And I know at least at the start he was also still doing high school classes, so while doing college classes. And I think there was some program worked out where taking the college class still got him high school credit. Because even here, we've had a few classes like that.
Like what?
American history.
Uh,
I mean, world history.
When I took college algebra, I did that. I did a
Yeah.
chemistry class, I got that. So,
You just have to work it out with the Hammer ladies, and they'll figure it out for you.
Cool. Look into that.
yeah, it's a great way to get started and to do some more exciting classes. Because the chemistry that I did was a lot better than my counterpart here that I had available.
Did you take it here?
No, it was an early morning class that Mr. D did,
Yeah.
Oh,
and so I went and did that so that I didn't have to retake biolab.
yeah. Smart.
And it was a ton of fun. He's a great teacher.
So I've heard.
Yeah, he's retired now, right?
Yeah. He retired right as I was about to take his class.
He was planning on it too.
It's too bad. COVID sucks.
Okay. Alright, so, oh, we didn't finish prom. Get distracted. 88.5 meters per second, 88.5 meters per second, that was part A. Part B. If the point on the rope, if a point on the rope is in transverse simple harmonic motion with a frequency of 2 hertz, so if we have a frequency of 2 hertz,
How many cycles is that?
how many cycles of the wave are there in the slopes, in the rope's length? So frequency 2 hertz, which means, so whoever's wiggling this, they're not just sending a jerk, so now they're wiggling it back and forth 2 times per second,
Okay.
right?
Mm-hmm.
So now this is going to create a sinusoidal wave in the sink. And the question is, how many wavelengths can we fit inside this rope?
Well, if it's 2 per second. Oh. If it's.
Are you trying to find lambda?
Well,
Yes.
how many meters does it travel in just one?
It goes 88.5 meters per second. We need to calculate the wavelength.
That velocity is the same?
Yeah, this is the velocity of the wave.
Oh, so we're looking for lambda? That's what lambda is?
Is the wavelength.
Oh, okay.
The length.
How
of it.
many?
Remember, if F, maybe here's a better way to think about it. If F is 2 hertz, then our period now is what?
1/2.
A half a second. Right?
Mm-hmm.
So our velocity then, times our time, gives us our distance.
Okay.
Okay? And so, good. And so, we calculate this, our wavelength is going to be just half of whatever our velocity is, and so our wavelength is approximately, I don't know if it rounds up to 44.3 or if it stays 44.2, it rounds up to 44.3.
Oh, that's pretty straightforward.
Because it's just half of that.
Yeah. Okay.
So you can get like almost 2 waves.
Almost 2 full waves. Remember, a wave is a start and end. That's 1 wave. That's 2 waves.
Okay.
So you can get, here's our wavelength. Our rope is 80 meters, so we get 80 divided by lambda is our answer.
Oh, I see.
That's how many waves we could get in the rope at once. Which is 1.81 waves. Okay. And that finishes the example problem. Any questions on that before we get to energy?
No, that seems pretty straightforward.
Shouldn't have erased that last picture. Shoot. So going back to our previous picture, nice simplified view of a wave. We were lifting a rope. That was our point B. Being pulled that way with some force F. And being pulled this way, we said with some force T. Okay, in this picture now, T, kind of made that really small relative to that. Let's make that bigger so we can see our triangle. So here's T, and so here is F sub Y, and then here is also F.
Mm-hmm.
If this over here were F, right?
Mm-hmm.
And so when we're calculating the amount of energy going through this rope, we need to keep in mind the work that we're doing on the system. And the work that we're doing is lifting the rope up with this force.
Okay.
Right? So it's going to be related to, so we're going to be very interested in that force. Now, I guess we're actually going to calculate the power, not the work. We remember what power is?
Energy over time?
Energy over time. Work per second, joules per second.
Joules per second. Okay.
And we're probably going to have to use a useful equation that we came across. So we said one of the ways that we can calculate power is work over time. That was one way that we typically calculated power.
Mhm.
The other way that we calculate power, and I told you it was more of a special case that turns out to be useful a lot, is force times velocity
Calculate power.
to calculate power. Remember that
Okay.
work is calculated with a force times a distance, right? Work is force times distance. When you divide that by time, you can rewrite that as force times x over t, which is how you get force times velocity.
Gotcha.
That's the intuition connecting those two equations.
Okay.
Make sense?
Mm-hmm.
So we're going to be calculating power, and so pretty sure we're going to calculate power this way, not this way. But either way, we're going to need this force. So the force that matters, the force that's going to be doing the work that's putting power into the system, is this F of y,
That's okay.
right?
Mm-hmm.
And so the first thing that we're going to notice here is that F of y over F, F sub y over F, which knows what that is, that's the slope of this line, kind of. It's a positive value that way, right?
Yeah.
F of y over F, and this is going to be equal to, here's the weird part, don't want to lose you, but we kind of specified it earlier, so maybe you're okay, delta y over delta x. We have a snapshot picture of our wave. Delta y over delta x gives me the slope of the function.
Yes.
Gives me the slope here. And notice that the slope here and the slope of this are going to be the same slope,
Okay. I
with
see.
one exception,
Okay.
minus sign, because this is a negative slope.
Still's the tension.
The tension, notice that the tension is in the negative direction, but this component is a positive number. We're just saying the length of this thing. So over here, we're just talking about a length over a length, a positive over a positive.
F is a negative.
Because we're not using the vectors. We're not using vector notation, we're using the magnitude of this vector and the magnitude of that vector.
Yep.
So that's a positive number, that's a positive number, positive, positive.
Okay, I see it.
And it's going to be the same as that if that number were positive. And so we need to put a negative sign there, so negative, negative gives us positive. Because our x direction is this way. Here's the point of the system.
Where's your delta y and delta x?
Remember, y is a function x of t.
Where is that on your picture?
Could be right there.
Then y is equal Fy.
Because anywhere for where our rope's in motion has the same slope. Doesn't matter where you calculate the slope along here, it's going to be the same, and it's going to be the same as this value, except negative. Does that not make sense? Not sure what I'm saying wrong.
How are you getting a slope out of Fy over F?
So,
How is that giving you the slope?
rise over run.
Oh yeah.
Okay, we're good now?
Yeah.
Alright. It doesn't click until it does, then it suddenly clicks. Okay, so that is F sub y, and then we also had our rope is moving up with some velocity V sub y for whatever part you want to talk about, right?
Yeah.
And so now the power that's going into our system, if we were to create a power xt, a power function, that tells you the power being communicated at some point, at some instant in time, then that is going to be our f sub y, which is going to be some function in terms of x of t, and it's going to be also times our v sub y, which is also a function in terms of x and t. We're going to make the substitution here in a second, but first I just want you to see how this is just power. We haven't substituted anything in yet.
Yeah, I see it.
Good with this so far?
Yeah.
making it kind of clear that these are functions in terms of x and t, but I could have just as easily written power is f sub y times v sub y, and that probably would have been clear for you. The point is just that v sub y here is 0, v sub y here is the same as here though. So there's a bunch of v sub y's here, and then over here it's going to be 0. Okay. And then we give it the freedom to change with time because maybe you start by lifting slow and then faster. Who knows?
Yeah.
Okay. So now we have this. So now we can make our substitution that we have over here for f sub y. Let's just write it out here. So now f sub y is equal to, maybe put the negative sign first, negative f times the partial derivative of y with respect to x. And we'll drop all the functional notation for a second here, if you're okay with that. So then we get that the power, our power function, maybe we'll keep this with an x and t, remind us it's power function, is equal to, when we make our substitution of f sub y, then we're going to get negative f times the partial derivative of y with respect to x, and then notice that the velocity in the y direction, that's the same thing as the partial derivative of y with what? With respect to t.
Yeah.
Right? That is what we mean by your velocity in the y direction. It's your change in y with respect to time. Oh, yeah.
Why'd you list out the functions like that? With
Sorry,
x
what?
and t? Why'd you do the functions with, never mind.
Right here?
That makes sense.
Just to remind you that these are actual functions, they're not just numbers. And so y is technically a function, y is technically a function, right? This f, on the other hand, is a constant. It's just whatever that force is right there. So constant, function, function.
Okay.
Good? Okay. So this gives us our instantaneous power at some instant in time and at some position on the road. With me?
At any position on the road.
Yes. Then here's how you would calculate the power being communicated at that point for anything. Now, if what we're talking about is a wave,
Okay.
if what we're talking about is a wave, then we know that our x function, whatever it is, our x function, is equal to a cosine kx minus omega t. Something to that effect, right?
Yes.
Not x, sorry, y. Y is our function here. Sorry. Same thing that we had right at the beginning.
Yeah.
Moving up and down. Here's our y function. And so we can calculate these values in the special case where we have a sinusoidal wave.
Okay.
Right?
Mm-hmm.
So now we know how to calculate those values. We already calculated that and that. But so we'll just try it out again. So then our power function is equal to negative f times partial derivative of y with respect to x. That one was, maybe put parentheses
Yes.
here.
We
We have negative Ka sine, negative Ka sine of kx minus omega t, right?
Yes.
And then for this one, we have times, put parentheses, that one is going to be omega a sine of kx minus omega t. Oh, no, those are both sides. Okay, we're good. Sorry, I thought I did something weird. Okay, so now we're just going to collect like terms with this.
Okay.
And so what do we get? We get the negatives and the negatives go out.
So everything's just positive?
So everything is just positive. I'll write the same order as if they do the F first. So we have F K omega times A squared times sine squared of Kx minus omega t, if we combine all like terms.
Can't you do more with that?
No, that's as simplified as it's going to get. So this gives us the power being communicated, the instantaneous power at some point at some time t.
Okay.
Now, what is the max power ever sent through? What's the largest this value can ever be? Well, that's when sine is 1.
How does sine get 1 though?
Sine fluctuates between 0 and 1, or between negative 1 and 1.
Yeah, I'm saying, what does your x and your t have to be then?
It doesn't matter. The point is, with some x and some t, this will eventually be
1.
1,
Okay.
or negative 1. When you square it, either case you get 1. And so this thing achieves a max at f k omega a squared.
That makes sense.
I did something wrong. What did they do? Let's see. So back, I have this fk omega a sine squared by using the relationship that omega equals vk. So they said, I'll put this up here for a second. By using the relationship that omega is equal to v over k, and that v squared equals f over mu, then they rewrote this equation as the square root of mu times f times omega squared times a squared. And then times sine squared of kx minus omega t. Okay, so let's really quick make sense out of that. What did they replace here? They got rid of k.
Mm-hmm. And that's it.
Okay, so let's see. Our substitution for k, when we come and we look at this, I know that k is equal to v over omega, right?
Yes.
From this equation, solving for k.
Mm-hmm.
And then I know that my velocity, I don't know why they said v squared there. We got our velocity is equal to this, right?
Yes.
And so this is equal to 1 over omega times the square root of f over mu. Did I do all that right?
Yeah, it still doesn't work.
Yeah, you get an omega squared.
Yeah, and that just cancels out because
Yeah, for some reason we need that to be reciprocal. I did something weird. Did I write down the relationship wrong? Omega is equal to v times k. Let's just make sense out of that really quick. What is k, our wave number? It's 2 pi over lambda.
E is equal to lambda times frequency. Since omega is 2 pi times frequency, frequency and 2 pi cancel out.
Yeah. So rewriting this equation to see how this equation is true. Really quick, we'll replace omega. We get 2 pi f is equal to v. We can rewrite as
do lambda times f.
lambda times f. That's what I was looking for. Top corner. Thank you. We can write that as lambda times f, and then k we can write as 2 pi over lambda.
So everything just.
And that cancels out with that. So you have safety on both sides. What? Okay, good. So that's where this relationship comes from. Now if we actually use that relationship right, we'll derive the right value for k. So k is equal to omega over b, which is equal to omega times, now this time it's the square root of mu over the square root of f. Right?
Square root of mu?
Uh-huh. So reciprocal,
Oh,
because
I
b is
see.
in the denominator.
Yeah. Okay.
Did I do something weird still?
No, it looks right.
Seems like Jeremy doesn't like it. What don't you like? Huh?
Oh, that makes sense.
Good? Okay, so now that we have the substitution for k, we come and plug that in right here. So we replace k with an omega, so our omega turns into an omega squared. We're going to get a square root of mu in the numerator. We get a square root of f in the denominator, but then f over the square root of f leaves me just square root of f. You see how they all cancel, reducing that to that?
Wait, how does f over the square root of f come to the square root of f?
Yeah, that's where I'm confused.
Okay. Is equal to
Oh, so, okay.
or another way to think about it is
F to the power 1, f to the negative 1 half.
1 f to the 1 half, that minus that equals f to the 1 half. I don't know. Whatever clicks best. Anyways, okay. So then we got this equation that they had. And so when they write out P max here, now instead of them writing it this way, they write it this way. Square root of mu times f times omega squared times a squared. And that's our max power.
So why is this useful and not just the original one?
Why is this useful and not this?
Why is the stuff we just derived any different from the first stuff we derived?
The first stuff we derived was the speed that the wave travels through the rope.
No, I'm saying that equation right there.
Oh, the power equation right here?
Yes, I'm saying
Why is it useful to know the max power that goes through a system?
Well, how is that the max power?
No.
Because the largest that this value right here can ever be is 1.
So that's
This
assuming
fluctuates
it's 1.
between 0 and 1.
So you took out of it, you didn't just. Okay.
So this is our equation for the power at any instant in time at any position. Here's the highest the power can ever be.
I'm saying we derived two equations for the power. I'm saying what's the difference between them and why did we
Here's
decide-
the equation for the power we're going to use, this final one.
That's the one we're going to use?
Yeah.
And that's the max one we're going to use?
And then this is your max power now, which is just where this is 1.
Why not just do force times k?
Why not just do force times k? I don't understand your question. Oh, you're saying why not use this equation?
Yeah.
It's just a matter of what variables are easier to plug into based off of what information you have.
Oh, I see.
Okay. Because now notice here, your max power depends on mu and f, which those are pretty easy to measure.
Your force and your density?
Your density and the force, how hard the string's being pulled, and then your omega, that just depends on your frequency that you're moving back and forth with.
What happens if you don't have a frequency?
Then you don't send in power. If you and Jeremy just hold either end of the ropes, no power sent.
I'm saying what happens if you just lift it up?
We assumed it was a sinusoidal wave. Here's your power in general. Now if you accept it's a sinusoidal wave, here's your power.
I see.
And here's the max power now for a
That makes
sinusoidal
sense.
wave.
Okay, I see
Okay.
where we're at.
What's the difference between mu and density?
The difference between what and density?
Mu.
Mu is density.
Why don't we use rho?
Okay, it's not technically density, because density is mass per unit volume, not mass per unit length.
So this only works with ropes and things like that.
Yes.
Whereas if you're trying to go through like a wave through a medium, you would have to use rho.
Potentially, yes.
So this doesn't work for
Sound?
sound.
Yeah, we'll handle sound next chapter.
So this is just ropes. And
This is not necessarily just ropes, but things that could be modeled like ropes.
Okay.
One-dimensional.
what does that look like in the physical world without being rho? Like what kind of phenomena happens like lipolysis?
Ropes for one.
Other than ropes.
Springs.
Springs follow this?
You and I could hold either end of a spring and I wiggle it up and down and send it down to you.
But it's all physical stuff where you have someone doing this.
Well, it could be someone doing it. Could be the wind doing it. Right? Could be any sort of physical phenomena doing it.
But it's a physical object moving up and down.
Yeah, moving back and forth and sending a wave through some medium.
Is a flag waving in the wind a wave?
I would not call that a wave. That's a mess of stuff. There's a lot going on. Tons of collisions all over the place with air particles hitting into it. So no, I wouldn't call that wave. That's a ton of collisions. Anyways, so here's the max power that we can center this wave at any instant. And the average power is going to be equal to 1/2 of that. Why 1/2?
Because you're going from 1 to 1.
1/2 happens to be the average of the sine squared function. So if you graph sine squared, that's a function that goes from 0 to 1. Notice that when you square it, you can't ever get negative numbers. So it's going to be something that looks like this. Whatever.
Yeah.
And we're not going to prove it, but sine squared has an average height of 1.
Okay.
And so, since this averages out to 1/2 and these other things never change, then the average power being center at is now 1/2 that. And so now we can calculate the average power center some sinusoidal wave. Okay, next we're going to talk about wave intensity. Wave intensity. And this one's easier to think about in terms of intensity of the wave. We're going to be jumping from 1 dimension to 2 dimensions, or to 3 dimensions for a second, when talking about the intensity of a wave. And the best example I can think about this for is, well, you could use light or you could use sound.
Okay.
Maybe we should do, is there an example? Let's do an example for almost what we just did really quick before we switch to intensity, because it's kind of a changing of gears. So we're probably going to need to use that average power equation. So we'll throw that up really quick. We'll do an example and then move on. 1/2 the square root, we have, it's a terrible mu. Mu of F times omega squared times the amplitude squared. Okay. Well, we can move on to talking about intensity. Erasing that somehow makes it.
Yeah,
More
it's
clear.
basically just plugging in your variables, right?
So intensity, you have a notion of intensity, how intense the wave is. How intense is the sound I'm speaking to you. Somehow hearing is meant to pick up intensity, how loud something is somehow correlated with how intense the wave is.
Okay. Wouldn't that just have to do with speed?
Not with speed. It would be like how much energy is in the wave. So as I talk to you, there's a lot of energy in the wave as it comes out of my mouth, but it loses energy as it goes out.
That makes sense.
Right? When I talk to you, notice that I could be surrounded by people in this room, and I could come stand here and I could talk, and I can talk to all of them. So a wave that was at one instance completely right here has now spread out and gone to everyone in the room.
Yeah.
So the same wave spreads out, spreads out, spreads out. And it becomes weaker and weaker and weaker. It loses intensity. Those waves are less powerful the further away it goes. And so it gets harder and harder and harder to hear me
That makes
the
sense.
further away I am.
Yeah.
Now your ears are calibrated so that when a wave is way more intense, it doesn't necessarily sound way more loud. Your hearing kind of works on a logarithmic scale, which means I have to talk 10 times as loud, or my waves have to have 10 times the intensity to sound twice as loud, roughly speaking.
What's the intensity like?
Huh?
What is the intensity?
Let's think about with a light source, because then we can think about intensity is basically how bright the room looks when you have a light source,
Okay.
right?
Yeah.
So with a light source, if you turn on one light, then how bright the room looks is a sense of how intense those waves are. And the bigger the room with a single light source, the less it does to lighten up the room. Because the photons spread out, spread out, spread out, and there becomes less and less and less of them to bounce off all the different sections of the room.
Yeah.
Right? If I take a light bulb in just a little box and look inside that box, it's really bright inside the box. But then if I use a single light bulb to light up the whole study hall, the study hall is very dim. It's not very intense anymore because those same waves have spread out, spread out, spread out. So that's an intuition for what intensity is. It's how much power those waves still have at a specific instance.
Okay.
Or like how many, like its frequency?
Sorry, what?
Like its frequency?
No, not necessarily its frequency. But you can think about more like its amplitude is dying down.
Like how far up it goes, the wave's getting smaller?
Yeah. They're going to jiggle less and less the further away they are. Because when I drew the picture of it, I drew the picture of this one collides with this one, collides with this one, collides with this one. I drew all the air molecules as though they were all in a row, right?
Yeah.
But a better picture would be something more like, because the sound spreads out as it goes, it would be more like this air particle hits both of these, and then those go forward and those hit these, and then those go forward and those hit these, right?
Okay.
And so the momentum of each individual atom halves each time in this simple picture I've drawn. If this has the same mass as this, and this has the same mass as this, when this collides with both of those, if it stops moving and converts all its momentum to both of these, they now travel with half the velocity that this one had.
Yeah, that makes sense.
So then why doesn't things like your voice or something dramatically decrease?
The intensity does dramatically decrease. It's just that your ears are calibrated so that drastic changes don't come across as drastic in your ears. So for example, when you're in a room and you turn on a light, look at how bright it is. When you turn on a second light, you double the intensity in the room, but it doesn't look twice as bright because your eyes are also calibrated. And your eyes recalibrate themselves depending on how much brightness there is.
Yeah.
Oh, that's pretty cool.
So it's your biology that's doing a lot of stuff for you that makes so that I don't sound twice as loud to you just because I have the distance between us. And I don't sound now twice as quiet because I double the distance between us. And so it's more like a logarithmic scale where I'd have to increase the distance between us by tenfold for it to sound for you to hear it half as well as you did before. Roughly speaking. That's not really what it is, but it's like that.
Okay.
But when you talk louder, that increases the amplitude?
Sure. It increases the amplitude, yeah. That's good intuition for it.
Okay.
Okay? So now we're talking about intensity, and we're talking about intensity from some source, like me, talking in a classroom. So here I am, bird's eye view, looking down on me. You guys are out here. There's lots of you, because this is a massive class with lots of students.
Okay.
And as I talk, my sound waves, initially my sound wave, so I just make a sound, try and make it as one pulse in a wave sound, whatever I can do. Initially, it's right here, right? All around me, kind of. I mean, it really comes out of my mouth like that and spreads out, but maybe we're fine doing that. We'll think about it as a cone. So I initially make the sound, and there it is. And an instant later, it's right there. 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 And it's dying down very fast. What was once there is now in all that area.
Yeah.
As that area of sound moves forward. And so it's dying down pretty quickly, right?
Mm-hmm.
And so the best way to write this is to think about, now we have a perfectly spherical speaker, right? Instead of me now talking, let's pretend that this is a perfectly spherical speaker, and it lets out sound all directions the exact same.
Okay.
Perfectly spherical, here's our speaker. When it lets out the sound, then all the sound, that's going to be like a sound wave, is going to be like a bubble around it, traveling out.
Okay.
And so all the energy that was in this bubble is now going to be in this bubble as it doubles its distance. That was meant to only be a double. Let me try and draw it a little bit more carefully. Like that.
Okay.
Anyways, so intuitively, the intensity at any point, the intensity here, whatever that is, or the intensity here of the wave, is going to be the power that the wave was given, because the wave still has as much power as it had,
Okay.
divided by 4 pi r, however far away it is. We'll call that r1. If we'll say we were talking about this one, so here's r1. That's too small. Let's trace that. Here's r1. 4 pi r1 squared.
Squared.
Why 4 pi r1 squared?
Yeah.
That is the surface area of a sphere with radius r. So all the power that was in that speaker is spread out across this ball. And it's evenly spread out. So you have this much power spread across this much area. That's your intensity.
But it's not all around you equally.
Well, for me talking,
Yeah.
right? But it still is like some portion of a sphere. You can think about some portion of the surface of a sphere, right?
Okay.
And then it grows to a bigger portion of a sphere, of the surface of a sphere.
Okay.
And it grows to a bigger portion of the sphere. And so it still grows at the same rate. Whatever portion of the sphere we had in the beginning, it keeps maintaining portions of a sphere.
Why is it spherical and not like moving and?
Because all sound travels out at the same rate. So if here's our source of sound, sound travels out from it at the same rate.
Oh, so if let's say you had a wall of sound that was flat and sound was coming out of it, then it would move kind of like in a rectangle?
I can get a wall of sound. You can get complex behavior really quickly, because what do you mean by a wall of sound? Because if you mean by a wall of sound, like I put a speaker here, and a speaker here, then you can actually get these waves. So this one sends out waves, and this one sends out waves, and those waves actually start interfering with each other. And so it gets really complex. And we'll talk about interference later, but
Is that the weird sounds you get when like listening to something and like a microphone or like a speaker interferes with each other or something?
no, interference would be if I had two speakers here. Now, they need to just be playing like a perfect pitch, because really when you listen to music, the sound waves are all over the place. It's not one perfect sinusoidal wave. But if we did have two speakers playing just one perfect pitch of a sinusoidal wave, then there would be places in this room you could stand if your ear source was just located at one point. Obviously your ears are spread out, and so how you take it in is more complicated. But if your ear was just a single point, you only had one ear and it was just a point, there would be somewhere in the room I could stick your ear so that you didn't hear either of them, because those two waves would perfectly cancel each other out.
That is pretty cool.
And there would be places that you could be where it sounds louder and places where it sounds quieter. And so amplifying these waves, oftentimes like theaters, good acoustics is designed about making so that these have the right interference with each other so that they don't cancel each other out but actually build on each other.
Yeah.
And so sound's able to go a lot further than it otherwise would have been able to.
Okay, that's cool.
Anyways, we'll get to interference.
Are we gonna get into it this section?
I think so. Principle of superposition, and then, no, I thought we did. No, it must be next section. Anyways, okay, so here's your intensity at I, the intensity of your wave at I, right?
Yes.
Or at 1, thank you, circle 1, here's circle 1, right?
Okay.
And it continues traveling out to some other sphere, circle 2, sorry, I know that's not a very good circle, but here's R2, right?
Mm-hmm.
And so your intensity at 2 is still going to be equal to, it's the same power, it was the same amount of power that you put into that wave. That wave still has as much power as it had, but all that changed is the sphere that it spread across.
Your radius.
Your radius, that's all that's changed.
It's exponentially decreasing.
Not exponentially,
Why not? It's got the square.
it's decreasing with R squared.
Isn't it
Ex-
exponentially decreasing?
No, an exponential is an e to the x type function. Exponentials are absurdly fast. 2 to the x is an exponential. If it was 2 to the r, that's an exponential, or 1 over 2 to the r. R squared and 2 to the r are very different things.
Yeah.
But when you plot a r squared, doesn't it go like the parabola? It just goes steeper and steeper and steeper. Isn't that
Yeah, parabola does get steeper and steeper and steeper, but it does not get steeper and steeper and steeper like 2 to the r gets steeper and steeper and steeper. For example, when we talk about a parabola, if we were graphing a parabola, if we go out here to 16, what's the point that we graph up here?
On a parabola?
Yeah. What's the equation of a parabola? Y equals x squared, right?
Yeah.
And we're just going to briefly compare this with y equals 2 to the x, just to give you some contrast.
Okay.
Y equals x squared, if x is 16, what's y?
Just at 16 squared.
16 squared, which is 256.
Oh, okay. Yeah.
Oh yeah.
Okay. Now, this is going to be roughly 64,000.
Oh, wow. Okay.
Yeah. I can see your point.
Very different numbers. Should have just done 10. 10 squared is 100, 2 to the 10 is 1,024.
Yeah.
But the further you out, the more grotesque the difference gets. It gets absurdly massive. This grows way faster than this thing. And you can compare their growth rates really quick. What's the growth rate of this thing? Y prime is equal to 2 to the x. It grows linearly. What's the growth rate of this thing? Y prime is equal to natural log of 2 times 2 to the x. Exponentials, their derivatives are still the same. Just changed by some constant. Times natural log of 2 or divided by natural log of 2?
I think it's times.
One of the two. Can't remember which it is for integrating or differentiating. But the point is, it's still basically, its derivative still grows the same as the initial function. And its second derivative and its third derivative, whereas the second derivative of this is already a constant.
Yeah. That's yeah.
Okay. Anyways, not sure what that detour was about. We were talking about intensity. So intensity now, this is the intensity at this circle, this is the intensity at this circle, right? So the ratio of intensities, I1 over I2, is equal to this over this, right?
Which is just
R1 over
R1
R2 over R1.
R2 over R1, good job. Right, because it's in the denominator of this one,
Which means it's
So- you gotta flip.
Oh, I see.
Okay. And so this is the inverse square law for intensity. If you know the intensity at one point and you're trying to calculate the intensity at the other point, here's how you do it. It depends on how you're changing the radiuses.
You have the intensity at one point, and you want to find the other intensity.
At another point. So if I know I1 and R1, and I want to know, okay, so what's the intensity going to be at R2, I can find I2.
Yeah.
Or if I know I know my initial intensity at some initial distance r1, and then I go out some unknown distance and I just measure the intensity again. I can figure out how far away I am.
How do you measure intensity?
You hear it when we're talking about sound waves. I mean, this is kind of like how sonar works, kind of.
Sonar?
How far away does sonar work?
I mean, you already have intuition of this kind of built into your head. How intense a sound sounds to you helps you map, when you have your eyes closed, the layout of the room around you.
Yeah.
Right? You know what you have good intuition for when your eyes are closed, for when I drop a book right there versus if I go some distance away from you and I drop a book and it helps you map out the room. That doesn't really work well because it echoes a lot, but you know, like the sound of people talking in general, and so you hear background noise that people are talking. You can kind of gauge how far away they are based off of the intensity of the sound. Just based off your own natural intuition. So, yeah, you can use the intensity to get a sense of how far away something is. Okay. Another one of those things that I really wish we could do, but we just don't have anything that we can wave. Because something cool to see, probably could just find YouTube videos of it. But, so, switching gears a little bit now, we're done talking about intensity.
Okay.
So I have a rope now tied to the wall. So I have a rope and we're sending a wave to it. Move that point. We're sending a wave through the rope. So my rope's tied to the wall there and I send just one pulse through it over to the wall.
Okay.
Now what's actually going to happen as that thing hits the wall?
It's just gonna go into the wall.
Where's the energy going to go? It can't just disappear. Let's say that this is an immovable wall. It's impossible to even vibrate the atoms of it. So the energy can't go into the wall.
So then it goes into a key.
Then it'll go back.
Oh no, it comes back.
It comes back. All right, you send the pulse down, and the wave comes back. All right?
Okay.
Now, how does the wave come back? Does the wave come back just basically the exact same as I sent it?
Wouldn't it come opposite?
What do you mean opposite? It's going to be a wave down, so you're saying after, when it's coming back. So the coming back picture, you're saying you think is going to look something like this?
Yeah.
What do you think? You like that?
No, I think they'll just hit the wall and go the same way that way.
So you think going back will basically look the same as it went?
Yeah.
And you think it's going to flip and end up at the bottom somehow?
Somehow.
Somehow? Good intuition. It's going to do this.
Okay.
Why is it going to do this? Here's why. Because as the rope comes to this wall, it's going to push up like that, right?
Mm-hmm.
And so the wall, to keep this place in point, is going to have to create a force downwards on the rope. So the rope's going to push up on the wall, so the wall has to do downward work on the rope.
Oh, that makes sense.
And so it's going to cause the rope to flip directions and come back this way. And so if you take a rope, tie it up, and send a pulse, the pulse is going to come back flipped over like that. Now what happens if instead of it tied to, we'll pretend that this is a pole, instead of it tied to a pole, I'm going to hook it around this pole with a frictionless ring. So there's a ring, frictionless, wrapped around the pole, so the ring can slide up and down the rope completely frictionless. Then what's it going to look like as it comes back?
Is it even gonna come back?
The energy has to go somewhere.
Wouldn't it go and just moving the ring up and down?
Okay, so it gives this ring some kinetic energy, then the ring loses the kinetic energy. Or does the ring go up and down forever?
Forever.
Forever?
I mean, that makes sense.
Wouldn't the ring going up and down send a wave that way?
Oh, yeah, duh. Okay.
So yeah, when you do the ring scenario, then the wave coming back is going to look exactly the same as the wave sent there.
That makes sense. Because it's moving.
It's going to go, yep, and it's going to cause ring to move up and down, which is the same as sending a wave that way now.
You know, yeah.
Okay. So, two different ways that we send waves, and it depends on what we call the boundary condition. Is the rope fixed at the end or not? It changes how the wave comes back.
Does it matter how much room it has on a rink?
No, we're just assuming it can move frictionless up and down. The ring was just a mechanism for making so that the rope can move up and down.
I mean, like, how far up does that matter?
It will move up as far as the wave.
What if it can't? Then what does it do?
Oh, then you got a mixed scenario of the end was frictionless for some point and then wasn't anymore, and then it became fixed. It's like a combination of the two scenarios.
But it still comes back down.
Yeah, it's got to send the wave back. The energy can't just disappear.
Okay.
Could you, by chance, like, flick it, and then real fast before the wave comes back, connect it to like another pole, and would it just keep going back and forth forever?
Sure.
Okay.
You don't even have to work that hard to get it. You just need to fix it at both ends, and then you flick it. And the thing will wave forever, assuming there's no friction. And you've noticed that on like a guitar string.
Oh, yeah.
Yes.
Oh yeah, 'cause it's fixed on both ends.
But you can also run and tie as fast as you can and see how that works. Okay, so next we have our principle of superposition of waves.
Well, when you flick it, when it's tied on both ends, does that send a wave in both directions? Or would it just send
Yeah.
one? Do you say yeah?
It sends a wave in both directions.
When they collide into each other then?
They interfere with each other. Yes.
So,
Next principle is called the superposition of waves. Let's get the superposition of wave principle. So imagine that you and Jeremy, once again, are holding either ends of a rope, and you both send wave pulses at each other. So here's the wave that you're sending to Jeremy, here's the wave that he's sending to you. So this wave is moving this way, this wave is moving this way. And you guys are holding your ropes.
Oh,
You with me?
yeah.
What's going to happen is these two waves collide.
Then it's gonna go up.
Are they going to cancel out, or is there going to be like some big super wave, or what?
It's gonna go up and then it's gonna stop.
So
what?
after the time goes by, you guys are holding the rope. So these things move. What's going to happen?
Yeah, it makes sense for it to go up and then stop.
So you think that they're going to combine to make like one big super wave? Like that? That was meant to be a lot bigger than those. Doing a very good job.
Yeah, and I'll do that and then I'll just stop.
And then a split second after that, you think the rope's going to look like that?
No,
Well,
because where does the energy go?
then I'll go back down.
No, just go down and leave the rope.
And then what?
No, it will go one way. Are they equal? Are the
Sure, we'll pretend that those are identical.
then they're just gonna hit into each other and cancel out somehow.
It'll go up and then it'll go back down.
But if like one's bigger than the other, it'll push
So
the
is
other
it going to
one.
end up
You're
like
talking
this?
about like perfect rope.
Perfect rope. We're talking about perfect rope. Perfect rope, perfect people, perfect everything.
Okay.
So what's going to happen is, you're right, it's going to go from looking like this to looking like this,
And it's
but then it's going to go to looking like this. And the waves are just going to travel past each other.
really?
So they don't even cancel each other out?
They don't cancel each other out. The waves just keep moving.
That's so cool.
And so the principle of superposition of waves, if you ever want to calculate a resultant wave, you literally just add the heights of the two waves together.
What about the wavelength?
Everywhere along the wave, just add the two heights together. So when the two waves were colliding, let's try and draw this. It's going to look awful, but we'll try. When your two waves were colliding, you had one wave, would have been some... That's just awful. One wave would have been something like this. So this was Jeremy's wave coming towards Peter, and then here's Peter's wave. When they start colliding, right? What does a resultant wave look like? You just add the heights of the waves together everywhere. So the resultant wave is going to, for the most part, follow this one right here. But then it starts getting some height from this one right here. So then it's going to start coming up even more. And then die down, and then reconnect. Can't draw very well. But here's the resultant wave that you're going to see. It's going to be some combination of both those waves together. So something that looks like that is going to be the wave that you see.
Okay, that
as they travel through each other. And once they get past each other, it's going to be back to looking like that.
Interesting.
So, next question then is, what about in this scenario? Jeremy sends his wave on the bottom, and Peter sends his wave, the exact same wave, on the top. What's going to happen with those two waves as they meet in the middle?
Okay, this time they cancel each other out, but then they keep going.
It's gonna bounce up.
They cancel each other out. So when they both meet, they cancel each other out, but then what?
They keep going.
And they just keep going.
No, and then the bottom one goes that way.
Oh, the bottom one keeps going this way, and the top one keeps going this way.
No,
Yeah.
They bounce.
They don't bounce off each other.
They don't?
No. They almost completely ignore each other. The waves themselves basically completely ignore each other. It's just that when they line up with each other, then you add them together, how you add their heights together, what you see is going to be the result of adding their heights together.
Yeah.
So it's called the superposition of waves. How do we write that as an equation? The height of the resultant wave is equal to the height of the first wave. That was meant to be y sub 1, where y sub 1 is the first wave, plus the height of the second wave. Superposition principle.
Okay.
Okay, so now, standing waves. And standing waves are what Peter just made reference to before. A standing wave is when you fix the wave so that it's fixed at both ends. So a standing wave is a wave fixed at both ends. So a common type of standing wave would be something like a guitar string. So here's a guitar string, and we take the guitar string and we pluck it right in the middle.
Mm-hmm.
And one of the things that would happen is when we pluck it, the guitar string would sometimes be up right here, and then it would flip down and come back down here, and it would oscillate back and forth like that.
Yeah.
And that's what the guitar string would look like. That's one way that the guitar string could look. Another way that you can see it is it might look like this. At one instant at a time, it looks like this, if you pluck the string. And then at another instant of time, it looks like this.
Time or position? Is this taking a picture of it?
Taking a picture of it. So at one instance, the picture could have been this line. And then at another instant, the picture could have been this line.
Is it ever flat?
Huh?
Does it get flat while it's
Yes,
moving?
yes. So the wave, you have the top and the bottom, they're going to move, get flat, come out like that, move, get flat, come out like that, move, get flat, come out like that.
So
So
it's
it's
doing
gonna be
super
one of
fast, so it looks like that.
Is it going to be one of those? Or is
Well, you can have it move like this, and you can have it move like this.
Depends on where you pluck.
it in the same strum?
Let's forget a guitar string for a second, because actually it moves at a lot of frequencies. Let's say that you and I are holding either end of a rope now, and we're going to maintain a perfect wave inside of that. One way that we could do that is you and I could move the rope up and down in unison so that it creates something like this,
Like a jump rope.
like a jump rope. Or I could move it up and down with a certain frequency that makes it start looking like this. And then I can move it up and down with another frequency that makes it look like this instead. And then it flips, and that goes up, moving back and forth like that,
Flips, yeah.
right?
Oh, so it just depends on your frequency.
So it depends on your frequency, and it can actually be a combination of frequencies going on that give it its functionality. Here's a string. So just some names really quick. We call the places where it's always zero, we call those nodes. So that's a node, that's a node, that's a node, that's a node. And then the places where it fluctuates the most, these 3 points we call antinodes. And we usually, yeah. So we label these, typically we label those with an A to say those are antinodes. And then we label these with an N to say those are nodes. And there's always one more node than antinodes when we have a system where the string is fixed at both ends. Now, I can't draw out this picture for you, just fundamentally see what's happening. When you have a string moving, when you pluck a guitar string and it's moving in this combination, up and down,
Okay.
a way that you could actually view it is, and I can't draw the picture for this, so you're kind of just going to have to take my word for it, is we have a string, and it's like we're sending a wave down this string, and it comes and it hits this end, which flips the wave, but it doesn't necessarily flip it at a perfect timing, so the wave comes like this, and maybe the wave looks like that by the time it reaches this end, which can't really do, but you have to kind of pretend with me for a second. Which would then flip it. The point is, it wasn't quite done finishing by the time it got to the end.
Yeah.
Which is then going to flip it, and so it's no longer going to perfectly cancel out, and so there's going to be a backwards wave that comes back this way, and then gets flipped and goes forward, backwards, backwards.
Okay.
So there's these waves moving forwards and backwards on here, and the combination of all those waves when you look at it is what creates this look, or this look, or this look.
Is that impossible?
It's very possible, and the author puts a lot of work into trying to make this make sense to you. He has a figure here trying to draw it all out as the waves move.
Yeah, but
So he's trying to show it a bunch of different times, and I can't draw it on the whiteboard. It would make a mess.
isn't it fixed on the right end?
So what you see looks like this. Something like this. Where it's just this moves down, then it moves like that, then it moves like that, then it moves like that. That's what you see. Right?
Okay.
But what's actually happening is waves are being sent back and forth on this scene. And the waves going this way and the waves going this way, when you add them together, cancel out to create this look perfectly. Go back to when we were talking about the wave impulses. When you and let's just look at one example. So when you and Peter sent waves at each other that were in the exact opposite direction, your wave being on the top like that, Peter's wave being on the bottom like that, pretend that those are identical. Here's the actual energies in the system. You have this wave down here, this wave right here, and those are traveling like that, right? And maybe these are at fixed ends.
Okay.
So at this instant, if someone were to take a picture, the stream looks like this. They're perfectly canceled out. Go forward some interval of time, what does the picture look like? So this wave comes this way, we'll pretend that this one was moving this way and this one was moving this way, right?
Okay.
So go forward some amount of time, so that they're not completely canceling each other out anymore, and what you're going to get is a little bit of a bulge down here and a little bit of a bulge up here. Something like that, right?
Okay.
And as it goes further and further, what's going to happen is, those are going to go out, and so then you end up with a picture something like this. Maybe. As those go completely to the point where they're barely reaching the ends, right? And then this wave is going to flip to the bottom, and this wave is going to flip to the top. So this wave is going to flip to the top and go that way at the top. This one's going to flip to the bottom, come up that way at the bottom. And these are the underlying waves actually happening. And what the rope actually looks like at different intervals of time, so it looked like this, and it looked like this, and it looked like this. And then it's going to go back to looking something kind of like that, except for flipped and kind of like that. What the rope actually looks like doesn't tell you what's fundamentally going on. It's these waves moving back and forth that are creating this look. So it looks like this, and it looks like that, and then it looks like that. Right? And so that's what's going on when you pluck a string, something like that. There's actually these frequencies of waves, a wave moving forward, and then it's hitting the end, getting flipped, and then moving backwards, going forward, moving backwards. And the way that those waves are perfectly canceling each other out is what creates these looks. And it turns out they always cancel out to create very nice looks. They always cancel out very nicely.
Yeah, I noticed that.
But is the bottom one fixed? Because the right end doesn't make any sense because it's supposed to be fixed.
Where the actual rope is fixed. But the energy in the rope, how much energy is at the top is this much, how much energy is at the bottom is this much, those perfectly cancel out to a fixed position. So this is meant to model the energies. It's like what the rope would have done if there wasn't this other wave.
At the
Kind of.
same second in time.
Yeah.
So when you get the crest on on the far right, then it's also at the bottom at the same time, which neutralizes it.
Yeah, and so the physical rope is actually at that fixed position.
And what does that one look like? The bottom one? Like, what would it look like?
If we tried to draw out what this looks like,
Yeah.
it would be very hard because we need to take the heights of these and add them together and plot that point.
It would have to be fixed.
Well, this and this would have to come out to, so if this was up an inch, this would have to be down an inch, so it comes out 0. Because that point has to be fixed.
Mm-hmm.
But then when we add these points together, maybe it goes up a little bit. And so maybe when you add it all together, you get something that looks like that. I don't know.
Okay.
Because I'm just drawing random stuff on the board that probably doesn't make physical sense. But your author, so he has that diagram on page 493, and he has the diagram trying to make it very clear to you that what you see the waves doing is a combination of the fundamental waves that are moving back and forth. So there's waves moving back and forth. You don't see the waves moving back and forth. You just see what they combine to look like, which is this right here.
Yeah.
Okay. Jeez. Yeah, we'll go through it. Considering you're skipping it, but we'll go through it. Okay. So let's actually look at some of the math for this now. So I'm going to be sending a sinusoidal wave down a string. So this isn't what the string looks like. I'm just going to show the waves I'm sending down the string.
Okay.
So I've got my string, and it's fixed at both ends. I'm going to send a sinusoidal wave down the string. And eventually, that wave is going to get flipped, and it's going to send a sinusoidal wave back, right?
Mm-hmm.
And those don't necessarily line up, and I don't want to draw them overlapping each other because I'll make a mess. So it's coming down as a sinusoidal wave. Eventually, it hits here, gets flipped, and it comes back as a sinusoidal wave. I probably should have drawn that the other way, like this. Gets flipped. Okay, that's what's going to happen if I send a sinusoidal wave down the sink.
Okay.
So, what the wave is actually going to look like to you is going to be a superposition of adding these two waves together. The wave on top going this way, and the wave on bottom that gets flipped and sent back this way.
Yes.
You with me? And so, the superposition principle tells us that it's going to be the wave on top, whatever that one looks like, plus the wave on bottom, and that's going to be our resultant wave. I don't know that matters which one I call positive and negative. But the point is, okay, so whatever it is, what we're going to end up with is yx of t is equal to, for the wave on top, they just changed the order. Let's see, how can I say this without confusing you?
Okay.
A wave that was moving in the positive direction was this. That was, we'll keep using the types of waves that we were talking about. Which ones do they use? Yeah. This was a wave moving this way, in the positive x direction,
Yes.
right? How do we model a wave moving in the negative x direction?
Wouldn't it just be negative then?
It's going to be negative that way, yes, because that negative comes from the fact that it flips. But just a sinusoidal wave coming this way is going to be a cosine of kx plus omega t. Now, how can I make this plus make sense? The minus here is what's ultimately shifting the wave to the right with time. And so the plus here is going to shift the wave to the left with time. And it's similar to if you think about this function, x minus 2 squared, that's a parabola shifted to the right 2, whereas x plus 2 squared, that's a parabola shifted to the left 2.
That makes sense.
Because I have to plug in negative 2 to get my 0. Here I have to plug in positive 2 to get my 0.
True.
So this is shifting a parabola to the right, this is shifting a parabola to the left.
Okay.
This is a wave moving to the right with time. This is a wave moving to the left with time.
Okay, that makes
Okay.
sense.
So I think we're ready for this now. So then the sum of the waves, the wave on top moving to the right is just going to be a cosine kx minus omega t. And then we're going to have plus the wave moving to the left. But the wave moving to the left is also flipped. It's y direction flipped. Notice that this gives me the y direction, the height of the wave.
Yeah, that makes sense.
Okay, so then we have minus a cosine kx minus omega t. Okay, that's what I was worried about, and so I think we're past the hard part of understanding this.
Wait, isn't it plus WT? Or
Oh, thank you. That was definitely a plus. Okay, so now right the way that the author has it written here, and it should be the same. So he does a negative cosine, not sure why he writes this one first, of kx plus omega t, and then we have plus cosine kx minus omega t. I think that's what he has. And we agree with it, right? We have the
Yeah,
same thing,
it
just
makes
different
sense.
order.
Mm-hmm.
Okay. So now, let's see. We can rewrite each of the cosine terms by using the identities for cosine and the sum and difference of two angles. So I know that, let's write these trig identities over here. Been a long time since we covered these. The cosine of alpha plus or minus beta is equal to, let's see, plus is plus. Cosine of alpha, I need to erase these trig identities are kind of long. Cosine of alpha, cosine of beta, plus or minus sine of alpha, sine of beta. Okay, so I think that's the only substitution that we need. And so here we have, this is equal to a times, so cosine of alpha plus beta. Cosine of alpha plus beta is cosine of alpha beta plus sine of alpha beta. So for a second, I'm going to replace, no, can't really do that. Sugar. We'll try it. So we have negative cosine of alpha, cosine of beta. And remember, we have this negative sign here, so we're going to have to distribute the negative to both these terms. So rather than plus, we're going to have minus sine of alpha, sine of beta. So that was doing this substitution for this term, distributing the negatives through.
Okay.
You with me?
Mm-hmm.
Yeah.
And then we need to apply it to this one. So then we're going to have plus cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. Okay. So notice that if I did this right, cosines cancel out. So that cosine cancels out with this cosine. Right?
Yes.
Huh?
Yeah.
Okay. And I'll pull the negative out while I'm at it from the sine. So it's going to be negative a times the sine of kx times the sine of omega t.
We have two of those.
Did I miss something?
We have two of your signs.
I have two of them. Okay. That's interesting. Minus 2a times that. Oops. Equals. Okay. So this now is just a sinusoidal wave, once again. So we can rewrite this as, this is equal to, all this this right here, notice that this is just amplitude of our new wave.
Yes.
So we're going to call that the amplitude of our, of our standing wave. The amplitude of our standing wave, whatever that is, times the sine of kx times the sine of omega t. So this is what our standing wave looks like. When it has a fixed end, well, yeah, with fixed ends. Let's see. The omega t, so we'll just talk about with the x, because that's what we want to take a picture of. Okay, so now notice that with the sinusoidal wave, so here is what the combination of the waves look like. This is what the string actually looks like as it's vibrating.
Okay.
Right? We just added the two waves together. That's all we've done so far.
Mm-hmm.
So that's what it looks like. So now let's notice where this thing is always zero. Where is this thing always zero? Because I told you that the way that these strings end up looking is if you've got it fixed on both ends, sometimes the string might look like that, sometimes it might look like that, but there's these points that we call nodes that are always zero.
Yes.
And they never jiggle. So we're going to find those node points. And notice that we're going to find where they're located on the strings. What are the x positions? Because this was taking a picture of the string vibrating, right?
Mm-hmm.
Yeah.
So this was x and y. So we're looking for the x coordinates that makes like this is always zero.
Okay.
Right? And so that's going to be wherever x makes this term zero. If x makes this term zero, then the whole thing goes to zero.
Yes.
Right?
That makes sense.
So it's wherever x times k is equal to some multiple of pi.
Can't you do the same with time? Say this is zero wherever time.
But we're specifically talking about the points on the string that never move up and down. So we're talking about the positions where the string never moves up and down. We're not talking about the times where at some point it's zero.
So you're treating time like a constant or a variable still?
No, time changes all over the place. We're finding the x's that makes like no matter what time it is, the string is still always at zero. So they never vibrate.
Okay.
So we're looking for particular x's that satisfy that.
Okay.
We're not looking for the time where the whole string is zero everywhere. Because if we were to do that, you're saying at what time does the whole string look like this? And there is a time that does that, and it's a time that makes this zero. Then the whole string looks like this. But we're looking for the points that never vibrate. So as the string moves back and forth, we're looking for the no points that never move.
Okay.
Probably good to clarify that difference. Okay, so x times k has to equal some integer of pi, some n times pi, some multiple of pi. Because any multiple of pi, sine is zero. Sine is zero at 0, at pi, at 2 pi, at 3 pi, at 4 pi, at 5 pi, etc.
Yeah.
That's where this comes out 0.
Okay.
Now let's remember what k is. K is 2 pi over lambda equal to n times pi, right?
Yeah.
For any n. We cancel out the pi's from both sides, and we move the lambda and the 2 on the other side. So x is equal to lambda over 2 times n. That's where all your nodes are. So take half your wavelength,
Yeah.
and remember, a full wave looks like this. Here's a full wave, right?
Yes.
So take half your wavelength, so only from here to here, and every increment of half your wavelength, you get a node, which makes great intuitive sense.
Yes.
Okay, so that's how you find the nodes.
What about your n?
N is any integer value. N is going to depend on your frequency.
What do you mean?
So you and I hold either ends of a rope. and I'm jiggling it up and down, right?
Okay.
There's going to be, maybe we can just demo this. Try it with the cord, see if we can reach it.
Is that even long enough?
I don't know, I didn't realize it was two put together.
Oh shoot.
Alright, we'll try it. Grab that end. Turn it back up. So, first off, there's a right frequency that I could. You don't want my God. You just hold still.
Okay.
There's a right frequency I could get this with. It just wants to spin like a jump rope. Can't get to just move up and down. There's a right frequency to maximize how this is moving up and down. And then if I do it with an even faster frequency, then I can get a node to show up in the middle. And this
I
isn't going to
saw
show
it for a
well.
little bit
You'll
there.
see it for a second.
Yeah.
We really need like long springs to do this with to make so you can really see it. But there's a right frequency I can jiggle it with so that it suddenly looks like this. And if I use an even higher frequency, I can make so 3 of those show up in it, and then 4, and then 5, etc.
So the higher your frequency, the more notes show up?
The more nodes you can get to show up. And we actually call those the resonant frequencies of the thing. And we've already talked a little bit about resonant frequency.
Yeah. But
The
what,
natural frequency, the frequency that maximizes the displacement.
what is
Okay.
the end's relationship to frequency?
The higher the frequency, the smaller your lambda, the more bigger n has to be to equal x.
So frequency is accounted for in lambda.
Yes.
And velocity.
So your nodes are going to be, if your string was infinitely long, then your nodes would be at 0, at half of lambda, or at, half of lambda, at lambda, at 3 halves of lambda, maybe write it that way better, etc. And that makes perfect intuitive sense.
Yeah.
If we were to draw out one of these waves with some frequency, who knows, enough that multiple wavelengths fit on there, then the nodes are at 0, at lambda halves, at 3 halves lambda, at 2 lambda, etc. Did I set down the marker I was using somewhere? I thought there were 3. This doesn't feel warm.
I don't know.
Neither do I. Oh well. Anyways, so those are where the nodes will show up.
Okay.
Okay, so now that's when we kind of ignore the length. So now if we fix both ends, and so we fix the length of this thing. Not sure if I need a bunch of this. We should be good with just that. So now let's talk about when we fix both lengths, or when we fix both ends, and so we have some fixed length, and we know what the length is. So I've got some length L now of wire fixed that we're going to vibrate, that we're going to put some frequency on.
Okay.
Since the ends are fixed points, the ends have to be nodes. Right?
Yes.
And so the possible waves that I can fix on here, the number of nodes I can have, is going to be L equal to n times lambda over 2, where n could be any number 1, 2, 3, 4, etc. My total length has to equal some number of, it has to be some integer number of half wavelengths, because it takes a half a wavelength for me to get back from one node to another.
Yes.
So it can be 1 node wavelength, or 2 half wavelengths, or 3 of them, or 4 of them. So the total length has to be some integer value of half wavelengths, if it's fixed at both ends, right?
Okay.
And so, if we do, really quick, if we make lambda as big as we possibly can, so we'll call lambda 1 our biggest possible lambda. What's the biggest lambda we could possibly have?
Just equal to L.
2L. The
Oh,
biggest lambda we can
divided
have
by
is a
2.
wave that is twice as big as L, and so only half the wave fixed on L perfectly,
Yes.
right? And so if lambda is equal to 2L, then our frequency one, the frequency that we would have there, would be the velocity that that wave is moving divided by 2L. Right?
Oh, so once you know velocity then?
And in general, our wavelength for the nth one is equal to 2L over n. Right?
Yes.
And so our nth frequency is equal to V NV. Put the n in front, they don't put it with the numerator. N times V over 2L to get your nth frequency. So the first frequency, to calculate the first frequency that we would need for some given length of material would be F1 here. And that would make so that there was just half a wavelength showing up. So that's the one that me and Jeremy did at first. And then I sped up, trying to get to F sub 2 to make 2 of those show up.
Okay.
And then F sub 3, F sub 4, F sub 5, any combination of these. And just to specify here, just to make it super clear, F1 is V over 2L. I can also write this as N times F sub 1. So all the possible frequencies that I could put on that thing are integer values of the initial frequency.
Okay. That makes sense.
Right? And so that's what's happening when you strum like a guitar string, something that's fixed on both ends, is it's fixed on the types of frequencies that can come out of that thing.
Which gives it its different sounds.
Which gives it its particular sound. Once, depending on the tension, first off, remember that the velocity here, velocity is equal to the square root of F over V, or over mu, right? And so there's two things you have on something like a guitar. One thing you have on a guitar is you can tighten or loosen the strings. That changes F. And then you have a bunch of different guitar strings that get thicker and thicker and thicker, which changes mu.
Oh.
Which changes the velocity that the waves move on that string, which changes the frequencies a particular string can give off. So one particular string once I fix that string, once I tighten it to a particular tension, it already has a fixed mass, it can now only give off fixed frequencies. I can't get any frequency off that guitar string that I want. It can only give me fixed frequencies. So when I strum that guitar, it comes off in some combination of fixed frequencies of its base frequency, F1. And so nothing weird happens when you strum a guitar. It doesn't suddenly give you all sorts of weird sounds that you didn't expect from before.
Yeah.
It can only give you multiple integers of that one frequency.
What about when you're putting your hands on like the frets and it makes the different sounds come out?
Okay,
Where's that?
so that's another thing that you notice people do, is they lower their fingers on the string, which then changes the length, which then again can change the sound.
Does it keep the same tension?
I would guess for the most part. I mean, how hard you're pushing
Yeah.
compared to how much those are tightened is almost nothing.
Mhm.
So it's really just shortening the length that the string has to vibrate on,
Which makes more frequency.
which changes the frequency.
Yeah.
In general, it's going to make the frequencies, it makes the wavelength smaller, so the frequencies go higher. And so it's going to be a higher sound as a general rule.
Yep.
Shorter strings make higher sounds, longer strings make lower sounds. Your low-toned instruments are in general longer than your high-toned instruments.
Yeah.
That makes sense.
What about like a rubber band? Does that sound high at all? Actually, it is kind of.
Well, again, it also depends on your materials and stuff.
Because of the density. see.
right? A rubber band isn't going to send a wave through it as fast as a guitar string. A guitar string communicates that wave very fastly, and so it has a much higher velocity.
Because of the force or because of the MU?
Because of the force that the tension you can put on that guitar string. You put that kind of tension on a rubber band, you're going to break the thing.
Yeah. But if you...
And so he also has that final equation, f sub 1. Another way that we could write it is replacing b here with this. And so he has 1 over 2L times that f over mu. And then f sub n could be an integer multiple of that for different instruments.
Yeah.
Okay. What time is it? I can't see the other hand. There's light in my way.
It's on the 3, so it's 15.
15. We'll pick an example problem to do.
Okay.
I don't know which one will be the most useful. Should we go back to like power, or there isn't one with intensity?
Well, I got intensity pretty well.
We could do with a standing wave one.
I think power would be a good one.
Go back to power.
Mhm.
Okay, we'll go back to the power one. Okay, so in example 15.2, of course, start by saying go find another page. Let's see what was 15.2 really quick. 15.2 we did last week. Oh geez, that was the one where we had to find like 20 different things. All right. At what maximum rate does Strachey put energy into the clothesline? That is, what is his maximum instantaneous power? Okay, we'll figure that out. So back in 15.2, we had Strachey wiggling basically a clothesline. And we knew that the frequency he was wiggling it with was 2 hertz. And we knew that the amplitude was 0.075. And we knew that the velocity that moved through the clothesline width was 12 meters per second.
Okay.
Our job in 12.5 was to find omega. Our job was to find the period. Our job was to find the wavelength. There should be enough information that we can recalculate those things if we need them. So let's just go back to this problem now. Okay. What is the maximum instantaneous power that we can have? So our equation for maximum instantaneous power, if we can remember that, it was the max power, P max, was equal to, and I'm not sure I can,
Of MU times the
square
force
root of mu times F
times omega squared times the amplitude squared.
Okay, awesome. So, let's see, we need omega, and then we're pretty much good. Oh, we need mu.
And the force.
The linear mass density is 1/4, so they tell us mu is equal to 1/4, 0.25. And they tell us that F is equal to 36 newtons. 36.0, maybe remind ourselves that we have 3 significant figures. They said 0.250. Okay. Okay, so our job is to find P max, and then P average is our next one.
That's really easy.
And then, Strachey tires, the amplitude decreases. What is the average power when the amplitude is 7.5 millimeters? What is the average power? And then so we find the average power again. But when A is equal to 7.5 millimeters.
Would that change the force?
No, same force, so he's still pulling this way the same far. He's just getting tired and not moving his hand as much. So before he's moving his hand like this, he's getting tired, now he's just moving his hand like this, but still pulling this way the same hard.
Nice.
So the force is all the tension.
The force is the tension at the other end of the clothesline.
Okay.
Okay. So, let's see. We already know how to calculate P max. Let's calculate that real quick. So P max is just the square root of 0.25 times our force, 36, and the radical,
What's your omega?
times omega. Oh shoot, we didn't find omega.
Yeah.
It's just
But-
2.5.
We have that, so 2 times pi times f, but we need all that squared. So square all the right stuff. Squared times our amplitude, 0.075 squared, is equal to 2.66 joules per second, or 2.66 watts. Okay, the average power is just half of that, which is 1.33, no rounding changed anything, so 1.33 watts. Now the average power when we change the amplitude, so I go and I change my amplitude here to be, rather than 0.075, it's 0.0075.
Yeah.
Squared, which is,
That's tiny.
yeah, point,
He's moving.
now I think I did something wrong. Yeah.
millimeters.
There we go. Now it's coming out how I want. This should be 1/100th of this. I don't know why I didn't try that. Or the average power here should be 1/100th of that. Since we decrease the amplitude by a factor of 10, then we decrease the whole value by a factor of 100. So it's going to be 0.0133 watts is our average power.
Oh wow. Guy must be pretty weak.
1.33 watts and then 13.3 milliwatts. Yeah.
Maybe shaking it less than a centimeter.
Okay. You want to do another example problem, or did you guys want to talk about any homework problems?
Did we finish homework?
I have questions on.
Okay, we'll spend the rest of the class going over questions.
Okay.
25